Welcome, everyone. I am incredibly excited to guide you through today's explainer. We're looking at a topic that honestly sounds like the plot of a sci-fi thriller, but I promise you it's entirely real. We're going to uncover this bizarre, almost hidden connection between cutting-edge quantum computers, idle Cold War nuclear warheads, and the surface of the moon. I know, it's wild. It's a massive puzzle of physics, geopolitics, and engineering. And the stakes? Well, they couldn't be higher, so let's jump right in. Okay, let's dive into this mind-boggling speed comparison. The world's superpowers and tech giants are practically tripping over themselves racing to build quantum computers. And there's one very clear reason why. Imagine a ridiculously complex cryptographic problem, like say breaking down a 2048 linked number into its prime components. A traditional classical computer? That would take an estimated 10,000 years to crack. But a quantum computer? It could absolutely tear through that exact same problem in just 8 hours. 8 hours! This is a total paradigm shift. It means whoever masters quantum computing first gets this massive game-changing strategic advantage in global cybersecurity, modern warfare, and even discovering futuristic life-saving drugs. But getting these machines to actually work requires something quite literal. They need to chill out. And by chill out, I mean they need an extreme physical environment. You can't just plug a quantum computer into the wall and let it run at room temperature, right? To unlock this incredible computing power and keep those microscopic qubits stable, the whole system has to be cooled down to 0.01 Kelvin. That is just barely above absolute zero. It's literally colder than deep space. Creating an environment that profoundly cold here on Earth is an immense physical challenge. I mean, how do we even achieve temperatures that low?
Well, that brings us to this incredibly specialized piece of tech, the dilution refrigerator. This is essentially the cryogenic heart of a quantum computer. It works by mixing two specific isotopes of helium, helium-3 and helium-4. Now, because of the different quantum statistics of these two isotopes, where helium-3 acts as a fermion and helium-4 acts as a boson, something pretty amazing happens. When you cool an equal mixture of these two liquids below 0.8 Kelvin, they spontaneously separate into two immiscible phases. It's kind of like oil and water. Forcing atoms to cross the boundary between these two phases absorbs energy, which then pulls heat away from the quantum system, driving the temperature all the way down to those necessary millikelvin levels. Now, what's really interesting about this is that the absolute secret sauce to this whole operation is helium-3. It's a stable, non-radioactive isotope with just one neutron. Because it acts as a fermion, it behaves totally uniquely at ultra-cold temperatures, making it essentially irreplaceable for quantum cooling. You literally cannot get a quantum computer down to 0.01 Kelvin without liquid helium-3. But here's the massive roadblock. Helium-3 is practically non-existent in nature on our planet. It accounts for a microscopic 0.001% of Earth's natural helium reserves. It is unbelievably rare.
And this scarcity brings us to a fascinating and honestly somewhat terrifying irony. If we can't find helium-3 naturally on Earth, where on Earth have we been getting it to run our current quantum experiments? Well, the answer lies in the Cold War. Our primary terrestrial supply of helium-3 actually comes from the radioactive decay of tritium. Tritium is a key element that is siphoned from idle hydrogen bomb warheads. So, ironically enough, it was the manufacture of nuclear weapons that gave us a steady supply of this rare isotope for decades. But as nuclear stockpiles are thankfully reduced, that supply of helium-3 is dwindling incredibly fast.
And this brilliantly illustrates the impossible bottleneck we're facing right now. Today, the estimated U.S. stockpile of helium-3 sits at a mere 20 kilograms. Just 20. Now, fast forward to the projected demand by the year 2040. With an estimated 10,000 new quantum computers coming online, and each one requiring up to 10 liters of liquid helium-3 to operate, the total demand skyrockets to roughly 4,000 kilograms. That's 4 metric tons. The demand totally dwarfs our earthly supply. So, how do we solve this? Well, this brings us to the first of two major solutions currently being pursued, and it requires us to look away from Earth entirely. If the Earth can't provide the secret sauce for quantum computing, we have to look to the stars. The first proposed solution is, quite literally, mining the moon. I know, it sounds straight out of a science fiction movie, but the physics and the business plans are very, very real. Why the moon? Well, because while helium-3 is vanishingly rare here, the lunar surface is practically covered in it. See, our sun constantly emits solar wind, which actually contains helium-3. Earth's magnetic field deflects this wind, keeping it away from us. But the moon doesn't have that protective shield. Over billions of years, the solar wind has just bombarded the lunar regolith, depositing an estimated 1 million tons of helium-3 right there in the moon's surface dust. Because of this incredibly vast, untapped reserve, private ventures are aggressively focusing on lunar extraction.
The bold goal here is to efficiently extract this helium-3 from the lunar soil, load it onto spacecraft, and actually transport it back to Earth. This wouldn't just supply those 10,000 quantum computers, it could also potentially fuel future nuclear fusion reactors, providing massive amounts of clean energy. Now, obviously, extraterrestrial mining will be incredibly difficult, wildly expensive, and fraught with logistical nightmares. But given the strategic necessity of quantum computing, it might just be absolutely essential.
Let's move to and see how this builds into our second option, because space mining isn't the only play here. While some are looking to the stars, others are mounting a terrestrial rescue mission. Solution 2 focuses on earthbound engineering workarounds. The idea here is simple, but definitely difficult. If we can't easily get more helium-3, we need to drastically cut down our current usage of it in non-quantum industries, saving every single precious drop we have for those dilution refrigerators.
To understand how we save it, we first have to know where else it's being used today. Helium-3 isn't just a quantum computing thing. It's heavily relied upon for national security and materials science. As NIST engineer Kevin Pritchard explains, helium-3 is the gold standard for neutron detection. At border security portals, detectors use helium-3 to spot stray neutrons emanating from illicit radioactive materials, like, the ingredients for nuclear bombs. Because helium-3's nucleus breaks apart so easily when struck by a neutron, its detection efficiency is around 95%. It's an absolutely vital security process, but it's eating up our incredibly scarce supply.
So materials scientists had a massive challenge. Find a replacement detector that doesn't use any helium-3. And they actually found it using abundant solid-state crystals, specifically a mix of zinc sulfide and lithium-6 fluoride. Here's the ingenious workaround they developed. When a stray neutron enters the system, it hits the lithium-6, causing the particle to violently break apart. Those highly energetic fragments then strike the nearby zinc sulfide, which causes the crystal to glow. That tiny flash of light instantly alerts the system to the presence of a neutron. It's this brilliant chemical chain reaction turned into a really digestible, highly effective detection system, all without using a drop of helium-3.
But this crystal method wasn't perfect right out of the gate. Initially, it was only about 30% efficient, which definitely wasn't good enough to replace helium-3. Electron microscopes showed the crystals were clumping together and blocking the reaction. So the crucial point is, by tweaking the concentration of the binding agent holding the crystal mix together and optimizing the crystal sizes, they achieved an even perfect distribution. This breakthrough skyrocketed the efficiency to over 90%, basically rivaling helium-3. Plus, because it uses a solid instead of a pressurized gas, these new detectors are thinner, cheaper, and can even be used deep underground for fossil fuel exploration. But most importantly, it frees up our dwindling stockpile of helium-3 gas to be used exactly where it's needed most, in quantum computing. We are currently standing at a truly fascinating crossroads of technology. On one hand, the sheer processing power of quantum computing promises to completely revolutionize our world. But on the other hand, that revolution is entirely dependent on an isotope so rare it threatens to halt progress before it even truly begins. We've seen how brilliant minds are tweaking crystal binding agents right here on Earth to save our microscopic stockpile, while others are literally drawing up blueprints to harvest the dust of the moon. It leaves us with a truly incredible thought to ponder. Will the next great leap in computing be cleverly engineered here on Earth, or will it ultimately have to be mined from the stars? Thank you so much for exploring this fascinating topic with me. Keep learning, and I'll catch you in the next explainer.